Good. Couple of preliminary remarks. First of all, I'm very eager to be interrupted. I don't think I function well as a lecturer when I'm not being frequently course corrected by the audience. So please, if not for your good, for mine, interrupt me frequently. And I'm going to be, I know basically nothing about the history of these matters. Indeed, Joost rightly pointed out that in a previous book of mine, the names of several of the important historical figures were misspelled. I mean,
it's UFFI.
So I know nothing about the history and won't make an attempt to pretend to here. I sort of feel like what I'm going to tell you is in a Boltzmannian spirit, but in that respect, I'm encouraged by what Joost pointed out, because it turns out that merely being inconsistent is being in a Boltzmannian spirit. But I think that what I'm telling you here is at least in one of the spirits of Boltzmann. And I'm also not going to be nearly as abstract as David Wallace was. David very beautifully sort of laid out a structure, a sort of, interpretation-free structure about whose interpretation one can then have debates. The way I'm more used to doing it is starting off with a sort of naive interpretation, laying out a picture of things, and then asking what would come out of a more careful philosophical scrutiny of the kind of picture one started off with. Okay. Anyway, let me start off with one very general remark about what I take to be the deep reasons why we need something like statistical mechanics of one form or another. In worlds that are even remotely like the one we live in, and I'm thinking in particular in this respect, in worlds in which it's the case that the sort of macroscopic objects with which we have the most direct empirical contact are combinations or upshots or something like that of enormous numbers of microscopic degrees of freedom. Okay. In worlds like that, it's plausibly going to be the case that a complete microdynamics, a complete set of laws of microdynamics, even if they're fully deterministic, maybe particularly if they're fully deterministic, are in general, and even if there were no problem about solving the equations, even if you were logically omniscient about these equations and so on and so forth, it seems to me a really important thing to emphasize that in worlds like that, in worlds like ours, the complete microdynamics and the ability to solve the equations of the complete microdynamics are in general going to tell you almost nothing about the way the world behaves. Okay, that is, they're not going to tell you basically. I mean, the intuitive idea is in worlds like that, there are always going to be microstates of the system you're interested in that are compatible with what you know about its physical situation, that are compatible with what you know about its macrostate, that are going to have in them all kinds of crazy correlations and conspiracies and so on and so forth, that are going to make them do crazy stuff 5 minutes from now, okay? The kind of stuff that these systems in our actual experience of the world don't do, okay? And if all you have is the microdynamics, so that if all you're able to tell yourself about this macro system is that you know it to be in one of the microstates compatible with that macro state, okay? The fact that among those microstates are going to be states that do crazy stuff, okay, is going to make it the case that the microdynamics by itself tells you basically zero about how this system is going to behave, or about what the world you're going to encounter is going to be like, okay? I think this is just plausible on the face of it, but something that's helpful in proving it is cases also like ours where the microdynamics happen to have some relevant kind of time reversal symmetry about them, okay? So that, for example, that makes it easy to prove that statements like I just made, which it seems to me are intuitively fairly compelling on their own, are in fact true. So, for example, we know that whatever the equations of motion of our world are, imagine, for example, the equations of motion of our world are classical ones, okay? We know that it's the case that there's a solution to those equations that describes a micro situation, which at a macroscopic level of description looks like a gas starting out collected in one side of a large container that spreads out to fill the container. Okay? Good. If we know somehow that the equations of motion of our world are classical, and we know from experience that there are evolutions in our world like this, it follows that this evolution is a solution to those classical equations of motion. But that also means, by time reversal symmetry, that there is necessarily a solution to those equations that takes you from the equilibrium spread out state back to the state concentrated in the corner, okay? Everybody see how all the details of this proof go? Maybe it's worth going through it step by step. There's a crucial step that sometimes doesn't get mentioned, which is the observation that the time reversed state of a state that's uniformly spread out throughout the container will be another state that's uniformly spread out throughout the container, okay? That is, for typical macro states like this, macro states that don't involve the system as a whole moving in one direction or another in the frame of reference you've chosen or anything like that, reversing all the velocities of the particles is in a state like this going to leave you in the same macro state as you were in before you reversed the velocities of all the particles. Everybody with me here? Yeah? Good. So we have an explicit proof in cases where the system is time reversal symmetric that that there are going to be things that the gas in equilibrium could do in the next 5 seconds or the next 5 minutes or whatever, compatible with the equations of motion, that these things don't do in our everyday experience of the world. Okay? And the fact that they don't do those is therefore something that it must be in principle impossible to extract just from the microscopic equations of motion. Okay? And so if we're going to have a set of laws that tells us in some interesting, informative way what the world we're likely to, what the world we encounter in our experience is actually like, in any world of this kind, where the macroscopic objects we encounter are in one way or another the upshots of the activities of enormous numbers of microscopic degrees of freedom, it's going to have to be the case that any set of laws that succeeds in summarizing those behaviors is going to have to include something over and above the microdynamics. Okay? And one way of saying, one way of talking about what's going on in statistical mechanics is that what's going on is some kind of a discussion of what it is we need over and above the microdynamics in order to give a picture of what the world of our experience is like, okay? In particular, what we're going to need over and above the microdynamics is some reason not to worry about, let's call them the perverse microstates associated with any particular macrostate. Some excuse for neglecting the perverse microstates associated with any macrostate. Okay? And having an excuse like that of one form or another is going to be absolutely crucial to giving a scientific account of what the world we actually encounter is actually like. Everybody with me here? And that's one way of saying very broadly. Oh, I'm sorry. Yeah.
So I was just wondering what you meant by what you meant by like over and above the.
Here's the claim. Just as a matter of logic, I have a system like the gas in equilibrium. I say, what's going to happen to it? Okay. Ask yourself what the microdynamics entails is going to happen to it. The answer turns out to be almost nothing. Okay. It certainly doesn't entail that the gas isn't about to recontract in the corner. It similarly doesn't entail that the gas isn't going to collect itself, in such a way as to form statuettes of the British royal family, or to recite the Gettysburg Address or anything like that.
So if I make a claim about epistemology, is that something over and above the laws? Or are you thinking it's like some objective feature of the mind-independent world that has to be added?
Yeah, I take it. I mean, we're going to talk about this, but I take it it's as much a feature of the mind-independent world as the truth of the microscopic equations of motion are. Right. That gases like this don't collect in corners, or don't tend to collect to abruptly collect in corners. Yeah. Okay. Or arrange themselves in the shape of the British royal family or anything like that.
But that seems like a slightly different worry to the one they had before, because like because an epistemic kind of claim is enough to give you a reason to neglect certain or maybe it's enough to give you a reason to neglect certain possibilities.
No, that's what we're going to need. Good. I don't want to prejudice the issue now. I guess I already did. I mean, I have a view about what kind of principle you're going to need to license your neglecting the perverse states. But you're going to need something. You want to tell somebody succinctly what the world is like, okay, by giving them some principles. Those principles had better, whatever philosophical category those principles end up fitting into, they're going to need to include more than just something like the microscopic equations of motion, and not because of the difficulty of solving those in practice, okay? Even if you could, sort of put that difficulty aside, you're still not going to be telling anybody anything very useful about what to expect of the world just by giving them the microdynamical equations of motion, okay? There's going to need to be, in addition to that, some reasons, some kind of guidance you give the guy as to which of the possible microdynamical motions to take seriously and which not. Okay? Yeah.
And just one quick thought coming from that is,
Sorry,
one quick thought coming from that is something like this. We have a whole bunch of dynamical regularities at a whole bunch of different length scales, and there's no magic one that makes the microphysical ones better. The hypothesis that somehow the microphysical ones underpin all the other stuff, it better not be a priori. It better be that you've got some kind of story that says how it is that they're interrelated. So okay, I take it the thing you're looking for is what's the thing that tells us.
Well, yes. I mean, one could. It's certainly not a priori that the most fine-grained ones or the most microscopic ones are in some way fundamental. But I think that's also broadly within the kind of theoretical tradition in which we're operating. So yes, as a purely logical matter, right? You're going to have, well, I mean, yes, you're going to want to know how those hook up. You're going to want to know how those hook up with one another. Yeah, I agree with that. I agree with that. This is right. This is keeping it interpretationally open to a degree which I'm not usually inclined to do, but yes, I agree with that as a logical matter. Good. Good. I take it at the most basic level, what's going on in a science like statistical mechanics is the provision of whatever it is we need over and above the microdynamical equations of motion to make those equations into a useful description of the world that we actually encounter. Okay? Is there a question? No? Okay. And exactly what form those need to take. In the context of classical mechanics, I think there are very straightforward arguments one can make, and probably we'll get into this more later on in the week, that the only sort of plausible form for those additional constraints to take is something like a probability distribution over initial conditions. How that kind of conclusion is affected by the transition to quantum mechanics, I think, is an interesting question and is something we'll be discussing later in the week. Let's stick with, for the moment, with the classical mechanical conception of this. And let's say one more thing. Insofar as claims of the form, gases don't tend to spontaneously contract into corners, are things that we regard as law-like claims about the way the world works, then these things that we're going to have to add to the microdynamical equations of motion are going to need to count as law-like as well. Okay? It's open for discussion whether one wants those macro claims to count as law-like or not. I think there are good arguments for thinking that they ought to, but we'll get into that more later too. Okay. So now let me jump right into some of the details of classical statistical mechanics, sort of at the point where Jos left off yesterday, although, as I said, in a radically less historically sophisticated style. So look, a big breakthrough. So we have this. So we have some system that we're interested in with some high-dimensional phase space, of which, as usual, we can only draw 3 dimensions. Really, not even that on a piece of paper, but you have to imagine much higher dimensions than this. And we have some carving up of this phase space into macro states, okay? Into states, say, with fairly determinate values of the thermodynamic parameters or something like that, okay? Good. So this thing is carved up into sections that are macroscopically different from one another. This is an issue we'll come back to later as well, but there ought to be 2 things one has, with 2 images that one has in the back of one's head when one talks about carving up the phase space into macro states. That is, there ought to be 2 ideas one has in one's head about what one means by a macro state. One is the sort of trivial meaning that you get from the word, which is they're states such that you can tell the difference between them without using a microscope, okay, or something like that, okay. The other is, and this is what David was emphasizing before, that they're states that have the feature that there's some sort of reasonably robust, reasonably autonomous science of such states, okay, like thermodynamics, okay, or maybe like dynamical extensions of thermodynamics, such as we were talking about yesterday, okay, such that you can say things like systems in this state 10 minutes later to end up in this state, okay, in this macro state, okay. The idea that those two notions happen miraculously or apparently miraculously to sort of roughly coincide with one another under a wide array of circumstances, on reflection, shouldn't seem like such a miracle. It's clear that if there are robust, if there is a way of carving up the phase space into these macro states such that you do get a reasonably reliable, reasonably robust, reasonably autonomous science of the behaviors of the macro states, there would clearly, to the extent that it's possible to do this, be significant selection pressure, say, for our sense organs to be sensitive to precisely those kinds of differences. Given that something that evolution is presumably not going to achieve is that our sense organs are infinitely sensitive to microscopic differences. If you're going to get them to be sensitive to something, it's going to be good to get them to be sensitive to something of which there is a fairly robust autonomous science. Is this clear? No? Everybody looks upset.
It's the science part. No.
Anything? No? Why does everybody look so awful? Okay. Good. And a great breakthrough, I take it this was of Boltzmann's, but I'm terrified to say anything like this in front of this audience. But I certainly grew up thinking this was a discovery of Boltzmann's, this famous combinatorial argument that tells you something amazing, okay? Something really, really important. That consider two possible states of a gas. Okay? A gas in a box. One state in which the gas is all in the corner, one macro state in which the gas is all in the corner, and another macro state, the equilibrium macro state, in which the gas is uniformly spread throughout the box. Okay? You take somebody off the street and you say to them, which macro description gives you more information about what the gas is doing? A priori, it's not clear why they're so different, okay? They both give you information about the density and pressure and temperature of the gas as a function of position within the box, okay? In similar degrees of detail, okay? One of them says that function is uniform. It has the same value at every point in the box as at every other point in the box. The other says it doesn't. It varies throughout the box. It's uniform within this little space here. The density is 0 outside of there. Blah blah blah. Okay. It was a great insight, I think, of Boltzmann that if you look at it, that the way this kind of macro language carves up the phase space is radically uneven. Okay, wildly uneven, okay? That is, that macro descriptions like this take up vastly smaller regions of the phase space, inexpressibly smaller regions of the phase space than macro descriptions like this do, okay? This is this famous combinatorial argument. Are people familiar with this combinatorial argument? Yeah? No? Anybody not? Boy, people aren't cooperating with my admonition to interrupt me here. Okay, let me suppose that people are familiar with that argument. So that, for example, draw phase space again. If we imagine, say, the energy hypersurface associated with a gas whose total energy has some fixed value, or some small thickness around this surface, like David was saying, in order to be mathematically more tractable. So imagine that this is the energy hypersurface associated with the collection of molecules in this box. What arguments like the combinatorial argument tell us is that the region of this energy hypersurface associated with this macro state is going to take up the vast majority of it. And this drawing is very, very inaccurate. That is the proportion that the equilibrium state takes up of this hypersurface is much, 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 much larger than what I've been able to draw here, okay? And that all of the non-equilibrium states, like this one here, are these teeny tiny little bubbles on the side, and so forth, okay? And so once you know that, and if you have any suspicions, for example, like Jos was mentioning yesterday, that maybe typical classical trajectories wander more or less ergodically over such hypersurfaces or something like that, it's going to become very, very clear that a trajectory that starts out here, okay, and wanders sort of at random, okay, over the hypersurface, where ergodic is meant to be a slight precisification of of an intuition of wandering at random, okay. Remember that ergodicity is the claim that as t goes to infinity, the proportion of time spent in any particular region of this hypersurface is proportional to the area of that region, okay. If that's the way the trajectories wander over the hypersurface, then a typical trajectory starting out in a non-equilibrium state is fairly quickly going to get itself into equilibrium and basically never get out, because there's no place else to go. Yeah?
So, two questions. One is, can you say a little bit more about what you mean by the state being typical? And second,
Right.
And second, as we were talking about yesterday,
Yeah.
I mean, there are reasons for not buying into this ergodic.
Sure. I mean, there are very clear reasons why not every trajectory could be ergodic. Okay. And we talked about some of those yesterday, right? And moreover, as Jos said, there are probably in many cases, I know there have been some actual proofs of ergodicity not for all trajectories, we know there couldn't be, but my impression is, you can correct me on this, that for, say, systems of 3 billiard balls in a rectangular box, we now have a proof that a set of measure 1 of trajectories of a system like that are going to be ergodic. Is that right?
That is right, but to be complete, the word ergodic has changed its meaning in the course of 50 years or so. In Boltzmann's original formulation, it was an hypothesis about the trajectory actually going through every point of the surface.
Right.
Now that's
right. No trajectory does that.
No
right.
trajectory does that.
Right.
But there's been a reformulation, especially after von Neumann's proof of a theorem, which he called the ergodic theorem, and which needed an assumption And the assumption, which was originally called metric transitivity, is that all the trajectories are such that there is no subset of the energy hypersurface with positive measure which will be avoided by the trajectory.
But moreover, there's a claim about the time as t goes to infinity.
That's the result of it.
Right. Oh, okay. I see. That's an assumption. Okay.
This is the condition.
Good.
Now, originally that has been called metric transitivity, but since it's a condition for the ergodic theorem, people have gotten into the habit of calling that ergodic.
Right.
So the original ergodic hypothesis has been replaced by a different assumption, which is still called. It's better to keep it, not call it the ergodic hypothesis, but it's still an assumption of ergodicity. And that assumption can be true for dynamical systems, even if the dimension is high of the energy hypersurface. But whether it actually holds for interesting systems is very much still an open problem, although for the case that David mentioned, for 3 billion volts in a rectangular box, it can be proved.
But all that having been said, the literal truth of the ergodic hypothesis is in all sorts of ways more than you need, and in all sorts of ways less than you need. Okay, it's more than you need in the following sense. Okay, the intuition is just that. The crude intuition is just that. Look, you've got this system, you've got its macro state. Okay, you say what's its evolution going to be? Appropriate answer, how the hell do I know? It depends on the details of the microstate, okay? And so you say, okay, but we need to guess. We need to do something. We need to make a little progress. You say to yourself, I don't know. I guess a typical one, whatever exactly typical means, okay, is gonna sort of wander at random over the hypersurface, okay? I don't know how to solve the detailed equations of motion. You want my best guess off the cuff. I would say that. Why would it end up favoring one region of the hypersurface as opposed to another region of the hypersurface? Okay? That's the sort of intuition. If something roughly like that is true, given the relative sizes of the equilibrium states to the non-equilibrium states that we have from Boltzmann's combinatorial argument, we're going to get the kind of result we want of approach to equilibrium, okay? Moreover, even if the ergodic hypothesis was strictly true and provable of certain systems, it wouldn't be nearly enough for our purposes, okay? Because it just tells us something about the limit as t goes to infinity. It doesn't tell us anything about how long it's typically going to take to get from, about relaxation times, about the exact sequence of other microstates that macrostates that you're likely to go through on your way towards equilibrium. So it's both way more than we need and way less than we need in order to actually do what we want in statistical mechanics. It's at best suggested, okay? That's the way I would put it, yeah.
So it's not clear to me why, barring our experiences of the macro world, why we would think that a path would just wander at random along an energy surface. Like it seems like we think, oh, this seems to work because when we look at systems of gases, that they often end up in equilibrium. So that's great. But
it's a little more than that. It's a little, once again, and real proofs of stuff that you want to know in statistical mechanics are few and far between. Okay. I used to have a math professor when I was in graduate school who would sometimes prove theorems by what he called the Jewish proof. Okay, and here's how the Jewish proof would go: you write the theorem on the board, you turn to the class, and you say, "It's not true. What's wrong with it? Okay, why isn't it true? Okay," and a lot of what we need to do statistical mechanics has to proceed via something like the Jewish proof. That is, you make something look reasonably plausible. You put yourself in a position where there aren't any obstacles, obvious obstacles to its being true. You can't analytically solve the equations or even perturbatively solve them or anything like that. You do the best you can. So I would say, no, it's not just that you make the assumption that it wanders at random. You combine the following things in your mind. You say, look, the microstate is very, very complicated here. How do I know what it does? First guess, it wanders at random. Next thing you do is you have some simple systems for which you can actually prove a claim like that, okay? And you have other systems for which you can prove claims that aren't exactly that, but are in the neighborhood of that or something like that. And until you can do better, of course, the right thing to do is to be able to actually solve the equations and see what's going on. In the absence of that, the kind of thing people do is scrape along as best they can, okay? You have a sort of pre-reflective intuition about it. Well, I don't know, what should I say, to be fair? I can't see any reason why it would favor this region over this region. So let it wander at random what you mean by at random is in a way that doesn't favor any particular region as t goes to infinity. And also you bolster that intuition with the fact that for certain simple systems which have some similarities to the kind of systems you think you want to study, you can actually prove theorems like that. And you take what you have and you get along as best you can. And you do a lot of proofs by the Jewish method. Okay. And that's the story. Yeah.
So presumably the combinatorial arguments involving like dividing space based on themselves.
Mm-hmm.
Doesn't matter how you do that carving.
Well, so here's the deal. What Boltzmann does. So Boltzmann does this argument in mu space, as I remember, or as it was taught to me. So here's how you. So remember, mu space is this 6-dimensional space rather than a 6n-dimensional space, where you represent the state of an n-particle system not by picking out a single point, but by picking out n points. Okay. So let me just draw 2 dimensions of mu space. Actually, to make it simple, let them both be position dimensions. Okay. So this is x1. This is x2, okay? Good. And you pick out a state of an n-particle system, or at least you pick out the values of these 2 coordinates for each particle in an n-particle system by drawing endpoints here. If the particles are distinguishable and you want to keep track of them, you should number each of the points. And that kind of numbering is crucial to Boltzmann's combinatorial argument. Then Boltzmann divides up the mu space into equal-sized squares. Okay, and he distinguishes between 2 kinds of information, both incomplete, that you could have about the arrangement of the various particle points in those squares. One he calls an arrangement, okay, which is a specification of which particles are in which squares, okay. The other he calls a distribution, which is a specification of how many particles are in each particular square without saying which particular particles they are, okay. It's clear that if the squares are chosen of an appropriate size, okay, small enough to count as microscopic, okay, but large enough so that in typical cases you'll have nice statistical distributions over those squares. If the squares are chosen of an appropriate size, a distribution is going to correspond to what we've been calling a macrostate, okay? A macro description. That is, a distribution is going to give you information, say, about a gas like this, about the densities and temperatures and pressures as a function of position within within the box of gas. Okay, good. Arrangements are not full microstates. Okay, but they give you more information than a distribution does. That is, they give you more information than a macrostate does. Everybody with me so far? So now Boltzmann makes the following simple, beautiful observation. He says, start out with the distribution. Oh, let me say one more thing. Number of arrangements, if all these boxes are the same size, number of arrangements corresponding to a macrostate is gonna be proportional to the volume of phase space corresponding to that macrostate. Okay? Because for each arrangement, for each particle, you have a volume in phase space like this, and they multiply each other. Is this clear? So it's number of arrangements that go with volume in phase space. Okay? So now Boltzmann makes the following beautiful observation. Consider the distribution in which all the particles are just in this box. How many arrangements does that correspond to? 1. Okay? We know for each specific particle which box it's in if the distribution puts all the particles in this box. Okay? Consider, however, the distribution corresponding to n-1 of the particles are in this box and 1 particle is in this box. Okay? That is, the distribution is just ever so slightly more dispersed than the original one. The number of arrangements that corresponded to the original distribution was 1. Okay? The number of arrangements that correspond to the new distribution is what? N. Okay? Because you could have chosen any of these n particles to be the one that was over here. Okay? So as the distribution gets a little more dispersed, the number of arrangements compatible with that distribution, which is to say the volume of phase space compatible with that macrostate, explodes exponentially. Okay? I might mention here that something that might be a little disturbing, especially if one considers these particles identical, is that there seems to be, it appears that the argument that Boltzmann is giving is assuming some kind of hexaetistic metaphysics, okay? Boltzmann is presuming that it's the case that even if these particles are identical, by permuting 2 of them, you get distinct possibilities about how the world could be, okay? And one might have all kinds of metaphysical reasons for denying that those correspond to 2 distinct metaphysical possibilities. I can just refer you to a beautiful paper from a long time ago by Nick Huggett, where Nick Huggett goes through the argument carefully and completely diffuses the worry that there's some kind of commitment to hexaetism in an argument like this. I think it's a really nice paper, and it certainly does appear on a sort of naive presentation of the argument such as I've just given you, that there's a worry like that there. And that would be bad, okay? It would be bad if somehow the truth of the empirical truth of statistical mechanics somehow settled the question of hexaetism versus anti-hexaetism.
Wouldn't that be really good?
It would be surprising. Let's put it that way. Okay.
Can I come back to the question?
Sure.
The answer to your question is yes.
I don't even remember the question. What was the question?
The question was, if I remember correctly, that whether the choice of the cells in mu space makes a difference.
Sure.
For how the story.
Sure.
So this is crucially. So, in this particular case, Boltzmann or David chooses a square grid. If you would choose another grid, you can get drastically different results.
You mean grids? Say a little more.
Won't we say it right now?
Say a little more right now.
Okay. And again, this is not just a hypothetical mind game. This is actually what Boltzmann did. He first takes a different choice. He chooses cells in U space, which are shaped in such a way not to choose the position and the momentum equal interval.
I see.
He takes position and sorry.
And energy.
He takes energy levels.
Yeah, this will be bad. Yes. Yes. Good.
So,
good.
say in the momentum space, the cells are now sort of consistent because energy is quadratic in the momentum. They consist of concentric spheres,
Right.
With equal increments in their radius. Now, in this case, the volume between the cells is not going to be constant over the cells.
Right.
Now, he goes through the same argument. He says, let's count the number of arrangements and see what the volume is that the macro states take up in phase space. And of course, there is one particular one that will have overwhelmingly more volume than all the others.
The highest energy. No.
No. But unfortunately, it's not
Right.
the equilibrium state.
Right.
It has a different
Right. Right. No.
So
absolutely
if
right.
that was your choice
Mhm.
of cells, and you would go through the same arguments, your conclusion would be that with overwhelming probability,
Good.
and if the dynamics is not all too crazy and even roughly ergodic, the system will evolve to the non-equilibrium state.
Good. Good.
So Boltzmann realizes at that point he's gotten a conclusion that he doesn't want.
Right.
So he goes back and says, hey, let's not take equal energy steps for our division of cells. Let's just take equal momentum
Right,
steps.
right.
So now they're going to be perpendicular in the
Good,
ordinary coordinates in phase space.
This is a really good point.
And then he gets where he wants. And then he concludes, so this choice must have been the right one.
Right. And there's an interesting, I mean, I'm going to want to come back to this in a little more detail in a minute. The way this was presented up to now, that is by me saying, you say stuff that just sounds reasonable. How the hell do I know what it's going to do? You know, it's going to wander evenly around. I shouldn't favor any region of the phase space over any other region. It has a sort of a priorist flavor, okay? We're going to want to discuss in a minute in detail that, in my opinion, this is a big mistake, and this is a good example of that. It's justified by its empirical success in the end. But let me reserve this discussion for just one more minute, and we'll be in a good position to have it. Oh, sorry, yeah.
The issue of the fact that we are taking that the trajectory is wandering and random.
Yeah.
It's possible that we are over the energy resource state.
Right.
Constrained there.
Right.
There can be many situations with different configurations,
Right.
momentum, and
Right.
position.
Right.
But anyway, I mean, I figure that the actual dynamics might don't lead to a.
No. You might. You absolutely might. Okay. This is what I meant by saying. You know, you do the best you can to solve the equations or to figure out properties of solutions. To the extent that you can't, you see if you can discover reasons why the trajectories might plausibly be excluded from some region of the phase space. If you can't discover any such reasons, you say, how the hell do I know? And I do have some simple systems that have some resemblances to the systems I actually want to study, like these billiard ball systems, where I can prove ergodicity, okay? I say, look, I have these systems that resemble the systems I'm interested in some ways where ergodicity is true. In the case of the actual systems, there's nothing obvious to me about certain regions of phase space, why they should exclude those trajectories. None of this, one should just say honestly what one knows, okay? I don't have the solutions. Of course, I don't have a proof that there aren't excluded regions of the phase space. I can't see any obvious reasons why some of those regions should be excluded. I have these other systems that are more calculationally tractable, where I can prove ergodicity, where I can prove that there are no such exclusions. I say, I'll make the best guess I can, given the information I have.
Okay, so an option speaking of the dynamics, whatever you start in phase space,
Yeah.
you end up in attracted in some particular region.
Well, attracted. Usually, when you talk about attraction, usually when you talk about an attractor, say in phase space, you're talking about a violation of the Liouville theorem. That is, that there's some region of the phase space which attracts all the trajectories into it, not in virtue of its size, okay, and so that they just get into it because they're wandering randomly. But even though its size is not so big, all the trajectories get sucked into it. In that sense, this doesn't count as an attractor, okay, in the way that word is usually used in dynamical theories. It's just the place where everything ends up because it's most of the surface, okay, and most is a wild, the ordinary English usage of the word most wildly understates the degree to which this is most of the hypersurface. Okay. Yeah.
Well, I mean, just to add to that quickly, because even stating that already has quite a lot of dynamics in it, even before we start asking where it wanders around, because to say the energy hypersurface already commits us to knowing something about dynamics. It's not true that this region occupies the most of the whole phase space.
No. Sure. We're taking on board what features of the dynamics we're able to calculate, like conservation of energy.
Exactly.
Sure. Yeah.
I'm curious to hear more about. So you've spoken about these simple systems, billiard balls, in which you kind of ergodicity.
I don't think that applies to any number of billiard balls. My memory was it was 3 billiard balls.
I think that's right.
Right.
But now I'm curious as to why you're looking more favourably upon these kind of toy examples when just yesterday I remember you offering another kind of toy example that was kind of easily seen to be not ergodic.
Yeah.
So
Yeah. No, but that's not an example of a system. That's an example of a state. Okay.
Right.
And what Boltzmann said about that state.
Can you remind us about these?
Yeah. Here's a clearly, non-ergodic trajectory of a bunch of, of a gas in a box. Okay. Suppose. So here's the box. Wow, I'm becoming sympathetic with everyone else's running out of time here. Yeah. Okay. Suppose you have a gas in a box. Okay. Imagine the following initial microstate for the gas. All the particles are lined up on the left-hand side of the box here. All of their velocities, they have no non-contact interactions with one another. Okay. They have to actually collide to have any interaction. And their initial velocities, I'm not drawing this very well, are absolutely parallel, like this. Good, they're just going to bounce up and down forever, okay? That's a stable cyclic solution to the equations of motion. If the walls of the box are absolutely straight, so on and so forth, that's a non-ergodic trajectory. Boltzmann rightly says about this, give me a break, okay? Yes, this itself is a non-ergodic trajectory, but the non-ergodicness of this trajectory is fantastically unstable, okay? Under even the slightest deviations, okay? Because if one of these particles is not moving straight up, but in fact at the slightest angle, it's eventually going to start to collide with the others. and everything's going to go straight to hell. Okay?
So maybe it was a mistake.
That is straight to ergodicity.
It was a mistake to me to have pointed to this example, but I take it there are other toy.
No, I take it at least what Boltzmann had in mind. I mean, I don't wanna in about 1 second, you know, okay, you'll see what I'm gonna do in 1 second. But no, I take it there was a general suspicion, and it would be interesting to get a counterexample to this. And I mean that we have discovered counterexamples in, well, I don't know enough about the history of this to say. I take it Boltzmann's intuition was that all of the obvious examples of non-ergodic trajectories were going to be inflicted with exactly the same kind of instability. Okay? And it's things like that he had in mind by thinking that typical trajectories are ergodic, okay? That you have to arrange things in a fantastically special way, okay? For example, and what you mean by fantastically special is, at least in the limit as t goes to infinity in your definition of ergodicity, the specialness would amount to these trajectories on any reasonable measure over the set of possible trajectories. These would be a set of measure 0. Okay, yeah.
Maybe it's worth mentioning at this point that there are dynamical systems which have the flavor of the sorts of things you think are real systems, which are provably do not have the ergodic properties, so they could decay AM theorem.
Right, that's right.
But there's also reason to believe, so those systems are not indecomposable. There are regions, once you're in the finite regions, once you're in them, stay in them. But there's reason to believe that as the number of degrees of freedom increases, those regions get really small.
Right.
Which does the work.
Exactly. Like I said, ergodicity is both much less and much more than you actually want to prove. Okay. And there are all kinds of senses in which it's much more than you actually want to prove. That is something close, something reasonably close to that is fine. The sense in which it's much less than you want to prove is that it doesn't tell you anything about times, okay? It only tells you stuff about the limit as t goes to infinity. You want actually much more information than that to get stuff about relaxation times and actual macro trajectories and stuff like that. Yes.
Yeah. I think it's perhaps important to distinguish between two cases. I mean, I very well agree with you that when Boltzmann has the intuition that really in a generic case you should expect the ergodic type of behavior, and yes, that there are counterexamples like that, which he explicitly discusses, and that
does he discuss that example?
Absolutely.
Oh, good.
Yeah. And that he neglects it because it's so wildly unstable,
right.
and that you could express his attitude by saying, "Oh, give me a break."
Right.
Although he doesn't have any particular exact proofs,
right.
He expects that the type of systems he is considering will generally be roughly ergodic. Might be some. However, the types of systems he is considering here are gas systems. It's just a container, and inside the container there are small particles. They're free most of the time, but they can interact when they collide. There might be hard spheres, like billiard balls, or there might perhaps be some other model. But that's the type of systems he's interested in. And of course, in those types of systems, so maybe a picture like that will be adequate, and you will expect transition to an equilibrium. There's no objection to that. But now, very often, people make a jump and say, this is not only true for gases, this is true for general systems. This is true for liquids, for solids, for everything in this room. Maybe it's true even for the entire universe that we have.
I'm about to make this jump.
Okay. Now, Now we have to go back to the same question.
Right.
Would we generally expect those systems to be ergodic? Well, one of the things, take a solid, for example. Usually the particles in the solid are bound to particular lattice size. They're not going to wander all over the energy hypersurface.
Isn't that just a bad choice of coordinates? I mean, the solid is also a phonon gas, and the phonon's going to wander around the coordinates.
Okay, yeah, but I mean, you have to be very careful.
Absolutely.
And they might find a description from the point of view which it could be, it could successfully launch a similar strategy. But I just want to point out, it's not that just because in gas theory we can have a sound intuition about whether the system will roughly be something like ergodic.
Right.
That sound intuition automatically can be carried over to.
Absolutely. Absolutely.
I mean, that's not just a hypothetical point, because we've heard a couple of examples like that already. I mean, if that were the energy surface of a bunch of carbon atoms at a certain temperature and pressure, and you said, look, here's a region of phase space in which it's a diamond, and here's a region of phase space in which it's graphite, it would be similar. The graphite region would dominate, but it's still going to sit there in its diamond state.
It's not going to sit there forever.
Not right.
Yeah. That's a question. That's a question about relaxation.
Right. But you said reasonably quickly.
No.
You did.
No. So look, but that's exactly what I meant in fairness to me,
right?
By saying ergodicity is much less than you want. Okay. Is much less than you want. Okay. It's not going to give you any information at all about relaxation times and so on.
I mean, having said that about the diamond as well, I take your point, but to some extent you might say that the way we generally handle metastability in these situations is to say, this system, which strictly speaking is governed by this Hamiltonian, blah, 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 we can, for very long times, neglect that and treat it as handled by this Hamiltonian. And on that dynamic idealization, it really is the space.
Right.
We're not allowed to make that move that everything is the thermodynamics of iron.
Right. Good. So now I'm about to make this enormous, precipitous jump. Okay. And by the way, just in answer to some of these other, I'm of course truncating the presentation of Boltzmann. Boltzmann had a lot more to go on than just this ergodic or approximately ergodic intuition. He had other approaches, like Jos was describing yesterday. He had the H theorem. He had all kinds of stuff. And they were all pointing in the same direction, okay? So the thought was there was justification, given what we were able to do and what we weren't able to do, to say, give me a break, okay? The stuff I have is pointing in the right direction. I see it from several different approaches, from the ergodic approach, from the H theorem approach, blah, 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 blah. Looks good, okay? Good. At the most general level, at the most general imaginable level, what's the claim that's being made to look good by these considerations? Or what's the claim that projects like these ultimately aim to make look good? Okay? I take it the claim that the whole project of statistical mechanics is ultimately aimed at making look plausible is some claim like this. Once again, as Jos pointed out yesterday, thermodynamics is a bad name for what these guys were doing in the 19th century. But take a more real autonomous science, dynamical science of temperatures and pressures and volumes and entropies and so on and so forth, where you have a whole bunch of dynamical claims about which kinds of thermodynamically specified macrostates evolve into which other kinds of thermodynamically specifiable macrostates, by which routes, over which times, so on and so forth. Okay. The claim which all this kind of work is broadly aimed at making plausible, I take it, is a claim like this. Take any such law-like regularity that we have, law-like macroscopic dynamical regularity we have, okay, to the effect that some macrostate A, okay, reliably evolves over a certain time period under certain external physical circumstances by a certain route into macrostate B, okay? The sort of ultimate aspiration, I take it, of all of this work is to make a claim like the following plausible. Corresponding to any such macrodynamical law, okay, whenever such a macrodynamical law holds, it's going to be the case that if you take the standard volume measure in phase space, okay, over all of the microstates compatible with A, okay, the overwhelming majority, that is the states that occupy the overwhelming preponderance of the measure, but on that measure that are compatible with A, are states that are going to be sitting on deterministic trajectories, which end up after the allotted time and moreover move by the allotted route to B. Okay? That in this kind of sense, all of the robust law-like dynamical claims about the evolutions in time of things like thermodynamic parameters are eventually going to be understandable at the level of the macroscopic on a model like this. Everybody with me here? Is this clear? Okay. Yes, and this constitutes exactly the kind of wild jump that was just referred to. And I don't even want to talk about the degree to which such a claim is justified by what we know today. That's presumably an incredibly long and complicated and maybe controversial story. Take it. I want to take it as given for the rest of this discussion, okay? Or I want you to imagine for the rest of this discussion that a claim like this has been made plausible, okay? And I want to discuss how to understand such a claim, what to think of such a claim, what such a claim ought to mean to our picture of the way the world is, and so on and so forth. So it's really important at the outset that everybody understand what the claim is. Everybody understand what the claim is? Yeah.
Just for this benefit of some of the students, could you say a little more specifically what that standard measure is and what's special?
Sure. Yes. The measure, so you take phase space. Here are three randomly selected dimensions of the very high dimensional phase space of some physical system of interest, okay? I don't know what, let these two be, position, two randomly selected position dimensions. Here's here's one of the momentum dimensions. There are 6n of these, if n is the number of particles in the system. There's a measure of volume in this space that suggests itself very naturally, and that has a kind of comfortable relationship with the dynamics. Okay. The ordinary Lebesgue measure on volumes here, where you take, where the volume of a region, where the volume of a cube like this. Well, I can't even draw it. Where the volume of a cube is just the the product of the lengths along of its lengths along the various dimensions. It's the case we have a theorem due to Liouville that if you start off, this is a very general theorem for any sort of classical Hamiltonian system, that if you start off with some set of points that fill a certain volume in that space, okay? You take each of these points is sitting on a deterministic classical trajectory. You just evolve it forward in time or backward in time. Put a dot where each of those ends up after 10 minutes. See what volume, see what region of space those fill, okay? We have a theorem due to Liouville that if you measure the volume in the way I just described, okay, the volume that the states after 10 minutes fill will be equal to the volume that the states initially filled. Everybody with me? Okay? So there are all sorts of ways. I mean, I think this word natural is dangerously and misleadingly overused. And maybe we'll talk about that more in a minute. But there's at least a naive sense in which this is a measure of volume that plays nicely with the dynamical equations of motion, blah, blah, blah. That's the volume I'm referring to, okay, when I talk about the volume measure over states here. Is that what you wanted me to say? Any other questions about it? The claim, not the claim, the hypothesis that we're entertaining for the sake of this discussion, that this claim has been made plausible, is going to sort of form the basis of everything else I want to say here. So I want to make sure that the content of that hypothesis is clear.
The hypothesis that it's made plausible isn't doing the work. The hypothesis is that it's true.
No. I don't think I said that. I said that the hypothesis that it's true is what I want us to imagine has been made plausible. Okay. Yeah. Was there? Yes.
Yeah, I was just wondering, how is this related to saying that all the initial states are equally likely? Is this the same?
Well, it's thought to be. It's a precisification of that. Okay, and we'll talk about this. Well, let's start to talk about it now. There isn't. Here's a fundamental fact of mathematics. Okay. If I have some discrete number of possible states, a marble might be in any one of 5 boxes or something like that. There's perfectly definite fact, a perfectly definite and perfectly unique fact about what it would mean to assign equal probability to the claim that the marble is in each one of those boxes. Okay. What you would need in order to make the content of a claim like that clear, in the case where the number of available situations is continuously infinite, okay, rather than countable and finite, as in the case of the boxes, is some kind of extension of counting, okay, to the continuously infinite case, okay? And it's the sort of fundamental discovery of the theory of measures. The theory of measures is precisely the mathematical project which studies possible extensions of this kind of counting to the case of continuously infinite sets. And the fundamental result of measurement theory is that there is no unique such extension, okay? That if you make a list of all the intuitive features of what it is to count something, okay, that you can think of, there are going to be many, many different measures that you can put on continuous sets, all of which satisfy all of those features. And features that you would have to add in order to distinguish between those measures don't have any intuitive, that don't have any sort of intuitive features to recommend themselves as genuine extensions of the notion of counting. So that the fundamental result of measure theory is that there is no unique way to extend that. There is no unique thing it means to say each of the microstates is being assigned equal probability, okay? There are many things that might mean. This is one of them, okay? And that, I mean, okay, yeah, let me start the larger discussion now. So let me back up a second. So in some crude intuitive sense, yes, these people, it seems to me, thought of doing this as giving each of the microstates equal probability. Why did they think that was the right thing to do, even? Suppose you could do it. Suppose there weren't these technical mathematical problems. Once again, I don't know the history here. I'm sort of reconstructing it for myself or saying something about how a lot of physicists feel nowadays or something like that. There is some kind of intuition going back to, at least to Laplace. I take it probably farther than that, but at least to Laplace. That goes under the name of a principle of indifference, okay? That says something like the following. It's a sort of a priori principle of reason, okay? That if what I know is that the state, that the situation is one of these, okay, where these may be a finite or infinite or continuous set of situations, but take first the finite case, okay, the discrete case. If all I know about the situation is one of these, okay, if my epistemic situation with regard to which one it is I have no clue, okay, then it's a mere sort of precisification. There is the following thought, that under circumstances like that, it's a sort of a priori principle of reason, that what you ought to do is assign equal probabilities to each of those situations. And I take it, I don't know if this is the explicit form of the argument that was made, but here's an argument that you could make. Look, there's only one assignment of these probabilities that, as it were, respects the symmetries inherent in the way you describe your epistemic situation, okay? The way you describe your epistemic situation is, I have no clue, okay? And I have no clue does not distinguish between one of these boxes and the others, okay? There are certain symmetries in your epistemic situation as you've described it. There's only one way to assign probabilities that respects the symmetries inherent in your description of your epistemic situation. That's the one, there's only one attitude, there's only one set of credences you could have in this situation that respects the symmetries inherent in your epistemic situation as you described it. That's the one where you put equal credence in each of the possibilities, okay? Yeah.
Can I just add a historical footnote with
Yeah.
respect to Laplace? Laplace says something like this, and then he says, but that supposes that we've got cases that are equipossible, and determining which ones they are is one of the most delicate points in the theory of chaos.
Well, okay.
So he's aware of the subtleties that later people.
If equipossible, I mean, there are I'm not sure I understand that statement. If equipossible just means equiprobable,
right,
then this thing is true by definition.
But yeah,
if equipossible means
right,
I have no better grounds for ruling this one out than ruling any of the others out, or ruling this one in than ruling any of the others in, then it's equivalent to I have no clue. And
right,
you have to be careful about when you really say I have no clue.
yeah, for Laplace, it's not absolutely clear what he means, but he seems to have some idea that there are some things that are harder to realize in nature, and some
Right.
things that are easier,
Fine.
and the things that are equally easy to realize in nature are equipossible.
Well, okay.
But he's aware that none of the difficulties associated with principal indifference would be used over Laplace. That's all.
Oh, well, okay. I have big difficulties with the principle of indifference.
Right.
I think this is a terrible argument. Okay. Is there nothing I could do? Is there no stance I could take toward the question of which box it's in that's compatible with I have no clue, other than assigning equal probabilities to each? Of course there is, okay? The other stance you could take is to say to the person, which part of I have no clue do you not understand? Okay? I have no clue, okay? The right thing for me to do is not assign any probabilities in this situation, okay? That, of course, also respects the symmetries inherent in my epistemic situation. And it also is, that is, I take it everybody has to pause for a minute. Maybe they pause in discomfort, or maybe they pause in wonder, okay? And it seems to me it's very natural to pause in wonder, but it's wiser to pause in discomfort. When somebody says, look at this magic trick I've done, just from I have no clue, okay? I get information about how to bet, about what the probabilities are, blah, 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 okay? There's something very puzzling about that, okay? That ought to give everybody pause.
Statistical mechanics is better than that. Just from I have no clue. I get information about the 10 times strength.
I got the whole deal, okay? I think this is a terrible mistake. Yeah.
So in like the marble $5 case you described, right?
Yeah.
So if you do use a principle of difference and apply and say 1/5 for each one, then you get what might be a result that we do want, which is that if you're asked what's the probability of it being in box 1 and 2 compared to it being in box 5, you say it's double the chance.
Yeah.
But if you say
why is that? That's not a result that
we
we do want. No, really. Yes, the right answer. It seems to me the right answer to all questions like that is, which part of I have no clue is it that you don't understand? I have no clue. I don't know.
It seems that's precisely a way of cashing out the idea that there's symmetry.
No, I don't understand. No, I don't get that. I don't get that. There is the symmetry that's inherent in my epistemic situation is a symmetry between all, between not only between propositions like it's in box 1 or box 2 or box 3, but it's in that subset. I have no clue. That's my epistemic situation. Okay. Yeah.
I mean, Wayne pointed out that the class is actually much less definitely pushing this than people attribute to him normally, and it's much more careful.
Yeah.
Actually, Poisson actually had simple examples where you would have 2 different ways of doing it, and
that's another
answers.
Right. That's
and
right.
So right away, his protege is bringing up real cases where you would.
That's absolutely right, but that's more akin to what I was calling a technical problem. That is, there seem to me to be 2 kinds of worries about a principle of indifference, okay? One is what I would call a technical worry, the other is what I would call a basic conceptual worry. The technical worry is that in lots of cases of interest, it's just not clear how to do the counting, okay? And particularly in cases of continuous sets of possibilities, there's a very deep mathematical problem with doing the counting. That's what I would call a technical problem. But it seems to me, in addition to the technical problem, there's an even deeper conceptual problem, okay? That even in cases where the business of how to do the counting is unambiguous, okay? The probability claims are not good translations of the basic epistemic statement, which is that I have no clue. I have no clue means I have no clue. Period. End of story. Okay?
Judging things to be equiprobable is not an absence of judgment.
That's right. That's right.
No, that's
okay.
right.
That's right. Yeah.
I see you struggling hard to make the point. I just want to tell you there's a literature out there that agrees with you completely.
That's nice. I don't think I was unaware of that. Right.
I've written a paper on it, and I think you're exactly right in what you're saying. I
Right.
was chatting here with Carl. Can I out you? Yeah, okay. He says, yeah, I'm writing on this as well.
Right.
I think,
No, good. I wasn't taking this to be an original point with me, although it is, in all kinds of circles, still a contentious point.
It is because there's this belief that that credences have to be probabilities, and they have more structure than you want in some cases. That's the difference.
So anyway, no, go ahead, please.
That's a nice example, or I think this is from Harold Jeffreys and Fisher discussing in the 1930s, and they have an example like, suppose you're going to meet somebody at the airport, and all you know is that he's either from France or from the British Isles.
Yeah.
Right?
Yeah.
And now the question is, well, the British Isles, is that Ireland, England, Scotland?
Yeah.
Or is it just the United Kingdom?
Yes.
France? Or is it?
I think it's
or is it
Keynes.
Is it
Keynes.
Keynes, yeah.
Yeah, it's Keynes, right? Yes,
Good.
you're right. Yeah.
So look, what's the upshot of this discussion? Okay, and I think it must have been, now once again here, this is a different kind of history than you do. This is what the history ought to have been, or something like that, as opposed to what it was. Okay, I take it that even, and I don't even know whether he was conscious of it, but some commitment like that must have been behind Boltzmann's claims to have, this is independent of the time reversal symmetry problem, to have derived, say, the increase of entropy just from the laws of mechanics, okay? In something like the Stossel-Ansatz, okay, not only was he adding a direction of time, he was making use of something like a principle of indifference, okay? And thinking of it not as a case of having added any additional postulate to or assumption, but having availed himself of an a priori principle of reasoning that it's inconceivable could have been otherwise. Good. The upshot of this little lecture is, to the extent that such a claim has been made plausible, it's an empirical claim, okay? And the way to think of these probability distributions is as empirical facts about the way the world happens to be, okay? It's true of our world, okay? I mean, one has to have a longer discussion now about how to interpret probability and so on and so forth, but very crudely and intuitively speaking, this is an empirical assertion to the effect that it's true of our world that if any large collection of systems in the state A, the proportions of them which are in this or that microstate compatible with A are going to be given by this probability distribution, okay? Is that an a priori truth? Is that a necessary truth? Certainly not. Why do we use it in our science? For the same reason we use F equals MA or anything else, okay? It's empirically successful. The character of this claim is not an a priori claim, it's an empirical scientific claim about the way our world happens to be.
So could
Yeah.
you just say again what the claim is, the exact statement of?
Well, no, I don't want to say because there's going to be a subtle discussion about what probabilities mean. Okay, but very crudely. Okay, here's an empirical. Let's put it this way. Part of what this claim means, okay, is that of any large collection of not prejudicially selected systems in the state A, okay, the proportion of them that are in this particular microscopic region, okay, is going to be proportional to the size of that, to the standard measure of that microscope.
See, that strikes me as way too strong because what we know empirically is that if you calculate the probabilities with respect to this measure, you get the right things.
Mm-hmm.
But there's going to be lots of measures that.
Oh, that's true too. No. I was trying to elucidate the content of the claim that this was the probability measure.
Okay.
Whether we need that claim in order to do our empirical work or can get away with a looser one is another question.
Okay.
And you're absolutely right about it. You're absolutely right about this. Yeah.
Sort of answer the question I was going to ask. You revised the claim from any large collection to any large collection that's not been selected in a prejudicial manner.
You're right.
Is there a slight worry that the way you spell out
It's going to be circular.
In a prejudicial manner is going to refer to the measure again?
No, hopefully not. I mean, I'm going to talk later about what conception of probability I think is fit to do the job of underlying all this. What sort of philosophical analysis of probability is fit to do the job of underlying all this? And so it's certainly going to be the aim of that analysis to have a non-circular way of saying things like this. But hold on to that question for a little bit, and I promise you we will circle back to it. Good. Should we take a break? I guess sure. Let me say one more thing about this probability distribution also, just about what its empirical content is. So, first of all, its content is empirical, unlike. What's the empirical claim that we want to make? That's a little dicey, and I want you to keep it in your head for a moment that a certain question about this, which I hope will be resolved a little later. So I said I was characterizing A here as one of those macro characterizations that turns out to be relevant to genuinely dynamical, thermodynamical kinds of law-like regularities, whatever those are. That's going to be important. That is, suppose we were to allow A to be some unrestricted characterization of a situation. I know this much about it. I don't know any more. Okay. So A is any proposition. Let A be. I think I used an example in my book 10 years or so ago. Let A be the proposition that a certain apartment has a spatula in it somewhere. Okay. There's a large ensemble of actual apartments that have this property. If I were to apply a probability distribution just like, if I were to apply exactly this probability distribution to the question of, is it more likely that the spatula is in the kitchen drawer than that it's in the bathtub, say, okay? The result I would get is, of course, that it's in the bathtub because the volume of the bathtub is larger. This is presumably of statistics of actual apartments with spatulas in them on Earth, empirically false, okay? And this is important, okay? The status that we're taking this postulate to have is an empirical status, okay? It's supposed to be actually descriptive of the world, okay? There had better not be a final form of this postulate that we arrive at, according to which the world we see in front of us is in some important way atypical of the ones picked out by that kind of postulate. So what counts as an A here isn't going to be unrestricted. We shouldn't expect it to be unrestricted because if it were to include apartments with spatulas in it, it'd be empirically false. Okay, keep that in mind for a few minutes. We'll come back to it. We'll come back to it a little later. Okay. So, with all this in place, what Boltzmann among the things that Boltzmann seems to have made plausible is that the vast majority, so take some non-equilibrium thermodynamic macrostate A, okay? Among the things that we're taking Boltzmann to have made plausible is that the vast majority, the overwhelming majority, by this standard volume measure in phase space of microstates compatible with A are sitting on classical mechanical deterministic trajectories, so suppose this is time, this is entropy, okay, are sitting on trajectories which take their entropy up in the way that we're used to from our everyday experience toward the future. Yes? Good. And that is, put a little more glibly, dangerously glibly, what Boltzmann takes himself to have made plausible is that it follows from the microdynamics, and maybe, although he wasn't explicit about it, from this probability postulate, that entropy always increases until you hit equilibrium, and then remains constant. And like Yost said, people said, how could that possibly be? Okay, how could you possibly have proven anything like that? The ingredients you used were the microscopic equations of motion, which are fully time reversal symmetric, and whether you were explicitly aware of it or not, in our reconstruction, I'm not talking about the history here, this probability postulate, okay? This so-called statistical postulate, I'll call it a statistical postulate, okay? Neither of those has any direction of time implicit in it. How could it possibly be that you derived a time reversal asymmetric law-like claim from these fully time reversal symmetric ingredients? Okay? That just can't be right. Okay? And of course, it's correct that it just can't be right. And here I'm once again, so this is a version not of how I know the history to have been, but how the history ought to have been, okay, or something like that, right? So Boltzmann comes back and says, in this version of how the history ought to have been, you're right. I didn't prove that. I couldn't have proved that, because that is a time reversal asymmetric claim, and only time reversal symmetric, and the starting point of this argument was in every respect completely time reversal symmetric. So you're right, I couldn't have claimed that. I couldn't have proven that. But I could have proven, and I claim I did prove, so says this imaginary Boltzmann, the following, okay? What I just said. Take some non-equilibrium macrostate A, okay? The vast majority of microstates compatible with that macrostate where I'm judging proportions in accord with this standard volume measure on phase space are sitting on trajectories whose entropy goes up toward the future, okay? How could it be compatible with time reversal symmetry that I've proven that? Here's how it could be compatible. Here's a way of critiquing what Boltzmann claims to have shown. Look, if you're right, okay, about this, exactly the same must be true toward the past, okay? Because there's nothing in any of your premises that picks out any particular direction of time, okay? So if you've shown that the vast majority of the trajectories originating in here go like this toward the future, you must also have shown, so we can grant you, okay, maybe this is what Boltzmann says, I have shown this, okay? You're right to point out that the fundamental time symmetry of all the premises of this argument entails that the same thing must be true to the past, okay? So that what I've actually shown is that the vast majority of microstates compatible with this macrostate, and I'll try not to say this every time I say vast majority, but I'll say it one more time, where by vast majority we mean with respect to this standard volume measure. What I've actually shown more fully is that the vast majority of microstates compatible with this macrostate are sitting on entropy trajectories that look like this. Okay, are sitting right at the minimum, right at the entropy minimum of whatever trajectory they're on. Everybody with me? Okay, good. It's clear that this part of the conclusions are welcome, okay, and correspond with what we see in the world, and it's equally clear that this part of the conclusions are deeply unwelcome and profoundly unlike what we see in the world. Yes?
I just wanted to clarify that comes from the time reversal theory.
Say it again?
Yeah, I just wanted to clarify that going up in both directions comes from the time reversal.
Going up in both directions, if I've got an argument in which a direction of time nowhere appears, okay, that this is what it looks like here, the same argument must also show that this is what it looks like here. Yes, so that's coming from time reversal invariance. Well, and let me say, I'm sorry, let me state the one other premise. I stated something like this before. The premise of this is, of course, that if I take any microstate compatible with A, and the premise is that A is the kind of state, but this is the kind of state you want. You got an ice cube sitting on the ground. You're asking about its melting properties toward the future or something like that. The premise, again, it's an important part of the premise that A is the sort of macrostate that has the feature that if you take up any microstate compatible with that macrostate, reverse all the velocities, you get another microstate compatible with that macrostate. Okay, that is taking the time reverse, maps this set into itself. Yeah, I'm sorry. Go ahead.
So this all seems a little bit fishy to me. I'm curious. Are you going to highlight how it is that you understand this statistical postulate?
Yes, we're gonna. But say more. Tell me more about what you're considering.
Oh, I'm just worried that this result is like this symmetric.
Oh no, that's a bad. I mean, there's no question that that's a bad result. Okay,
right.
But that's an unwelcome result, and I want to talk about at least 3 respects in which that result is unwelcome. But I mean, is what you wanted to. You just wanted to point out that this is an unwelcome result, or did you want to say something more?
Maybe, and I'll add that I'm curious how it is that you're understanding these probabilities. So at the moment, I want to take the following attitude. Okay, but this is certainly not an attitude I want to stick with. Just for the sort of smoothness of the presentation. At this point, if somebody says, what do probabilities mean? The answer is going to be, give me a break, you know what probabilities mean, okay? Of course, nobody knows what they mean, and I'm very much going to want to, a little later on, talk a bit about a serious philosophical analysis of probabilities that's fit to undergird all of this stuff. But yeah, for the moment, I just want us to be getting by on everybody's ordinary, no doubt incoherent, intuitive conception of what probability talk is about. Okay, but a question of a deeper philosophical analysis of probability, I agree, is particularly crucial to this kind of a discussion. And if there's time, which I think there will be, we're going to talk about it. Okay. Good. I want to talk about 3 senses in which this result is unwelcome. And what the hell? Let's go all the way here. Let's think of A as representing not the current macro state of this or that particular subsystem of the universe, but the current macro state of the universe as a whole. Okay? Good. 3 senses in which this is unwelcome. 1, it's wildly empirically false, or so we think. Okay? That is,
if this is the current macro state of the world, the claim that this is its trajectory, is the claim that there was never a moment in the history of the world where I looked younger than I do now. Okay, there was never a moment in the history of the world when any of the ice cubes that are now half melted on the floor were less than half melted. They were all previously more than half melted, just as they are going to be more half melted in the future. That is, this is the claim that broadly, speaking in broad thermodynamic terms, the past of this moment is more or less the mirror image of its future. Okay, and this is something which we take to be empirically, wildly, obviously false. Okay, that's problem number one. Yes.
It's just, this isn't about the talk. Should we close that window?
Oh.
I think it's.
Sure. You mean just to get the air conditioning?
Yeah.
Yep. Let me try.
It's
It's a separate question. Can we close it? Yes. Good. Good question. All right.
It's going to open again.
First problem, this is wildly empirically false. Second problem, it's not just, it's worse than that it's empirically false. That is, let's go through this a little more. Somebody says here, wait, what the hell is going on? I mean, how could this be the past? I have photographs of myself now in which I look much younger than I presently look. I have distinct memories of this ice cube on the floor being less melted than it was 10 minutes ago, so on and so forth. It's important to notice, okay? So here's a trajectory, say, in which the ice cube was less melted 10 minutes ago, okay? In which there was once in the world a person who looks like the photograph I currently have, so on and so forth, okay? But this trajectory is associated with, by this standard measure, vastly fewer of the microstates compatible with this macrostate than this trajectory is, okay? So if I say to somebody who tells me, who does this calculation and concludes this must be the trajectory, what the hell are you talking about? How do you explain my memory of the unmelted ice cube? How do you explain this photograph that I had in my hand, that I have in my hand now, which depicts a younger looking version of me, so on and so forth? The guy says, I explain it as a sort of fluctuation out of equilibrium, okay? It collected together. The photograph was a long time ago much yellower than it is now, and before that it didn't exist at all. It fell apart into pieces, so on and so forth. You're likely going to respond to that by saying, give me a break. What are the chances of that? How plausible an explanation is that? And the cute thing here is that the guy has a very nice answer, which is, it's fantastically more plausible than explaining the existence of that photograph by your once actually having looked younger. I can explicitly calculate the probabilities of those two scenarios whereby there came to be a photograph in your hand, okay? And the one where it formed out of goop, okay, by chance, although the probabilities are very low starting from equilibrium, they're fantastically higher than the probability that it came from here, given that the information you have now is that this macro state obtains, and you use this probability distribution. Yeah?
I mean, just a small point. I guess forms out of goop isn't quite the right thing to say. I mean, the trajectory on the left isn't a by chance goop trajectory, it's a time reverse of an ordered trajectory. So
right.
The really likely thing isn't that it kind of came into being whoosh, it's that it kind of smoothly.
No, that's what I'm saying. No. I mean, it was goop a long time ago, like I was saying. The likelihood is that 10 years ago it was yellower, but still in existence. Yeah, absolutely right. That is, the likely story of how it came to be here is exactly the mirror image of the likely story of what it's going to become. Okay. And the cute thing about this dialogue is, if you say, what the hell are the chances of that? the guy says, boy, that's exactly what I was hoping you were going to ask, because I can calculate the chances of that, and they're much better than the chances of it having gotten here by your scenario. Everybody with me here? Okay, good. But the trouble is that, so this is the second worry about this. First worry, it contradicts what we take ourselves to empirically know about the past. Second worry, slightly deeper worry, look, among the things we take ourselves to know about the past, among the things we're sitting now with records of in our heads, on pieces of paper, so on and so forth, are, for example, the very experiments by which we became convinced of the truth of the microscopic equations of motion in the first place. Okay? So that taking the sort of standard statistical mechanical way of calculating, which gives us a trajectory like this, it's something worse than merely being in conflict with what we take to be our empirical data about the past. There's some kind of deep cognitive instability at that point in the space of possible attitudes toward the world. Okay, because becoming convinced on the grounds of the microdynamical equations of motion, or on the grounds in part of the microdynamical equations of motion, that the entropy curve looks like this, undermines the very idea that you have good reasons to believe in those equations of motion in the first place. Everybody with me here? Yeah? No? Questions? Comments? Expletives?
I just didn't follow it. Just say it again.
The claim that this is the trajectory, okay? Follow the reason. Somebody says, how the hell did you come to believe that this was the trajectory? I said, well, I have good empirical reasons to believe in the microscopic equations of motion. I have all these experiments, blah, blah, blah. I have records of these experiments. I also have good empirical reason to believe of the same sort in this probability distribution. I combine those two. They tell me that the trajectory looks like this. Okay, but then somebody says, but wait a minute. The claim that the trajectory looks like this means that among the beliefs you have about the past that are false are the beliefs that you ever did these experiments that convinced you of the truth of the microdynamical equations of motion and the probability postulate.
So you're just deepening really the first worry, which is the
Yes.
false memory worry.
Yes, yes, but the false memory worry is so here's a claim. There isn't any sort of reflective equilibrium available at this spot here. Okay, you can't there isn't any way of telling yourself that you have good reasons to believe that this is the actual entropy trajectory, okay? Because among the things about the past that entropy trajectory denies are true are precisely the reasons you cite for believing in those equations of motion in the first place, okay? So there's a sort of deep cognitive instability associated with taking yourself to be here, okay? That isn't something that you can coherently do. Yeah?
So I'm just sort of wondering why there's the privileging of like the present macro state of the world in this way, and it just seems like, I don't know. So someone might go, oh well, you know, it's equally consistent with all your evidence that everything kind of formed by this sort of time reverse decay than that, it's in fact more consistent, more likely given your evidence,
right.
That it formed that way than that it formed by the way. Particularly, what happens if you respond by just saying, well, sorry, that like it's just not true that my evidence consists of present memories.
Right.
Like my evidence consists of, you know, like amongst my, I don't know. It's not clear to me that I've less confidence in my memory that I was in this room 5 minutes ago than in my like.
In my confidence that I'm here now.
Yeah.
Right.
Yeah.
I think that's right. For the moment, we're just playing a sort of formal game, okay? Suppose that what we take is given. And this is not a formal game completely without content. That is, one can imagine, whether one can justify it at the end of the day is another question, but one can certainly imagine taking as a starting point okay, from which one can certainly imagine taking the attitude that, that I don't know what I can see right now of the present macro state of the world or something like that, taking that as more directly epistemically available to me than sort of claims about the past. Whether at the end of the day that would be a justified epistemic procedure is a good question. The better thing to do is to find a way, of course, of not having to make a decision like that, okay? And that's what we're going to talk about in a minute. But I agree with you. For the moment, take it that we're playing a formal game with those rules. Take that as given what would follow from it, okay? Somebody else said, yeah.
I just want to say that you make this a deep cognitive instability. There's really nothing cognitive about it. There's an argument that starts out with certain premises and ends up with the negation of the premises, right?
Yeah.
That the evidence for, you present the evidence for whatever you have, and then you keep going through, and then one of the conclusions is the evidence is false.
Right.
It's nothing cognitive here. It's
no, but I don't know maybe I'm misusing the word cognitive. It's not clear where that should leave you, except that this whole train of reasoning left you at a dead end.
Let's call it reductio.
No, okay. But good. That's fine. I'm perfectly happy to characterize it that way. Yeah.
Harvey, did you have something first?
Oh, well, I had something to respond to Neil, but yeah, couldn't you just say, assuming we only have evidence during our lifespan,
right?
Just pick, say we have evidence up until backwards in time, up until the time we were born,
right?
And then you just run exactly this argument for retrodictions before the time you were born.
Yes, that's right.
So it doesn't really matter about the epistemic feature.
Oh no, that's true. But suppose you took this attitude even toward distant galaxies that you could. But yes, the farther back it goes, and even the farther back it goes into my own biography, there certainly is a sense that what we're calling inference from what's directly epistemically available to us is playing a larger and larger role. So just a simple extreme way of making that explicit is to limit yourself to the present evidence. Yeah.
So I just want to expand the logic of what's fine. So these disastrous retroditions are a consequence of taking seriously the idea that this probability distribution is the right one over the microstate.
Plus the microdynamic.
Plus the microdynamics.
Right.
Now, we got to that.
Assuming this, okay? Assuming everything works out.
So we got to that probability distribution by noting that we're not supposing it's given to us by a principle of difference.
Right.
We rightly rejected that.
Right.
And so it's given to us by, we have empirical evidence that using this one gives the right answers.
Right.
Which is really evidence that, what our evidence is really for is that the right one, if there is a right one, is in the class of probability distributions that gives us that.
Yes, absolutely right.
And a good reason to believe that among that class, this one, the one that gives us disastrous retrodistributions, is not the right one.
All of those are correct.
Okay.
Okay. All of those are correct and beautifully pave the way for my next step.
I think perhaps one might add, at least in the way you present the story. So we have the supposition that some claim has been made plausible about this.
You mean like this?
Yeah, that's
right.
At least for a certain way of carving up macro states.
Yes.
And in the way you present the story, it is assumed that pictures of yourself and particular states of consciousness in which you find yourself
are all characteristics of those. That's correct. That's absolutely right, and good to point that out. Yes, all of that is being supposed. Good. What are we going to do about this? So look, here's a way of approaching it which picks up on what Wayne said.
You're going to give us three things. So
I'm sorry. Here's the third. Good. Thank you. Good. Thank you. Actually, that's really important. Third worry. This is not only seems empirically false and self-undermining. Okay, that is subject to a reductio in the way you were saying. It also seems internally self-contradictory. Okay, that is, it can't be that every time is the global minimum of the entropy trajectory that we happen to be on. Okay, this could only consistently, forget about the issues of evidence and so on and so forth. Okay, this could only mathematically be consistently be applied at one moment in the history of any trajectory. Okay, because every moment where it is applied is going to entail that that's the minimum. Okay, so it's just flatly mathematically inconsistent to apply this statistical hypothesis.
Sure, isn't the right conclusion that it's much more probable at any point later on that you're at a minimum? It's not absolutely assured, and that there's some.
No, it's not absolutely assured.
Because there is a mathematical structure here that can be consistently described.
Sure. But take it. Now translate probabilities naively for the moment into some crude frequentist interpretation, okay? And ask, so I have a whole, I have a whole bunch of ice cubes. That are half melted at a certain time t, okay? That according to this probability hypothesis is going to entail something about the frequencies with which certain microstates are realized among this ensemble of ice cubes. Okay, good. Let them evolve forward. Okay, until they're 3/4 melted. So each of them becomes 3/4 melted. Okay, then apply the same postulate to them there, okay? That's going to entail that the vast majority of the ice cubes are now in fact in microstates that entail that they weren't half melted 10 minutes ago, but that they were fully melted 10 minutes ago, okay? That's the sense in which it's contradictory, okay?
Yeah, I just think you're on that one. I back off on that.
I think you should. What saves it from inconsistency, or at least, is that you've drawn a circle A,
right,
which represents a certain set of microstates.
Mm-hmm.
Now, the next circle you draw for the second application of the argument is not the same set of states.
No, it's a different. But the claim is this is some macrostate B. Okay, take the uniform distribution of microstates compatible with that macrostate. Most of those are sitting on trajectories like this.
Yes.
Okay, that applied to the ice cube explicitly contradicts the claim that most of the ice cubes here came from this. Okay, that's going to say that most of the ice cubes here came from this.
Yes.
Okay.
But the set of states B,
yeah,
is not the same as the time evolved.
The set of states B, if this postulate is true, no, the set of states, that's exact, but most of the states in A go into B. Okay.
Yes. But there are many more stats in B.
That's exactly one of the reasons why it's inconsistent to apply this at every time. Okay. That's exactly I agree with that 100%.
I just take out the not and say that's exactly why it's consistent to apply it every time.
No, I don't. No. I mean, you apply it. No, this seems to me wrong and important to clear up. Look.
Can I add something?
Sure.
I mean, so you've drawn a little portion of this curve here.
Right.
So imagine that the universe is mostly in equilibrium with occasional fluctuations.
Right.
And the bigger the fluctuations are, then the rarer they are. There'll be all, along that line, there'll be all kinds of guys who find themselves in that state B.
Yeah.
And the vast majority of them will be near a local
Yes,
entropy maximum.
that's correct.
So that's, I think, what these guys are saying. That's
correct, but that's different than what I'm saying.
Okay.
Okay? I'm talking about the consistency of applying this rule, okay, again and again, along the history of some actual system or ensemble of systems, okay? And asking that it characterize the frequency with which certain microstates are realized, okay, by that ensemble of systems throughout its history.
I think it's just the first guy coming back again. You seem to be telling me you have to believe that as you move up this curve, you have to believe at every moment that your memories are false and that most likely you came from a higher entropy state by fluctuation. It seems to be the same guy just coming back.
No, well, no, but I don't understand. Once again, suppose that, I guess I'm not sure I understand what you were saying in the last sentence there. Here's the claim, okay. What's inconsistent, okay, what's explicitly inconsistent, if probabilities have anything at all to do with frequencies, okay, is that you take a bunch of systems that start here, okay? That's what characterizes the ensemble you're dealing with, okay? They all start here, okay? And you ask, if this distribution properly characterizes the frequencies of microstates with which certain microstates are realized in that ensemble at this time, could this distribution correctly characterize the frequencies with which microstates are realized among that ensemble, the one that came from here at the later time?
And what is B? That's just the
B
time.
is, let A be a collection of ice cubes that are unmelted.
Yeah.
Let B be a collection of ice cubes that are half melted.
Okay, so that.
But a collection that came from these.
Yeah. So
That
now
came
I'm
from
proving that
these.
because the B that I was thinking was the set of all states through which those trajectories are passing.
The set of all states through which the trajectories that came from
including the ones from the higher entropy states.
Yeah, no, but that's exactly not. But what I'm telling you, the way we're defining our ensemble is that it starts here.
Yeah. Okay. But so I'm not seeing the inconsistency then, because there are two senses of
no.
What,
So here's
that B circle might be.
the following claim must be false. Okay. The claim that an ensemble of systems whose frequencies of microstates are correctly described by this at this time. Okay. The frequencies of microstates of that ensemble, the one that came from here, will be correctly described by this at this later time.
He's right about that.
Okay. That statement must be false.
That statement is false.
Yeah, that statement is false.
What's the this that you pointed to the second time?
The uniform distribution over B.
Right.
Okay.
Yeah, I agree with that.
Good. Yeah, good. That's all that's being said. Okay? That's all that's being said. In the actual history of our universe, okay, or of ensembles of universes that share this, okay, this couldn't be consistently applied to every
Just
time.
to make sure I understand why, it's because that B is going to include...
It's because most of those B's come from here, as you rightly said. Okay,
right.
that's exactly the point.
Okay, so the inconsistency is between what and what?
The inconsistency is between applying the probability distribution at this point, okay, and applying it at this point to the same set of systems.
So it's an inconsistency between the known dynamics presumed for the system globally, which is fluctuating, and the rule that says that state A evolves to state B such that...
No. Can I try? Think of the case of free expansion in a box. You initially have a gas confined to one partition, and you put the uniform distribution over that. Pull the partition out, let it act to equilibrium. I say, okay, now new equilibrium state, I apply the uniform distribution compatible with that new macro state. well, that's going to give high probability to lots of states that it wasn't in because
Right,
it's
I understand that. I'm just asking, where's the inconsistency? Something has to contradict something. What's contradicting?
Here's the,
having a probability distribution that gives vanishingly small probability to the set of states that you a moment ago said it was certainly in.
right.
Yeah.
Right.
Say it again.
That's
And then I'll show you.
Having both those probability distributions be the correct distribution over microstates is inconsistent.
One
Yeah,
is
but
saying
they're different sets.
No, but that's what I'm telling you isn't true. I'm talking about, the claim is that both this and this, okay, could be correctly descriptive of the ensemble that's defined as the one that started here.
The conditional
That's
on the thing
all.
having gone through.
Okay,
Yeah,
that's it.
Yeah, that's right.
That's it. That is applying this probability distribution, applying this principle at every time in the history of some specific ensemble. Okay, this kind of probability distribution, what I'm calling a statistical postulate, can only correctly describe such an ensemble at most at one moment in its history.
I don't see that.
Oh,
Maybe
you
right
should.
about that.
Yeah.
Because the uniform ensemble at one time doesn't evolve into a uniform ensemble
That's right.
at a later
And if
time.
you,
Right.
this
Sure,
is
I
terrible.
understand that, but I'm just waiting for the
do
inconsistency.
batting probabilities. I just want to do a batting.
Okay, probability assignment plus the dynamics is inconsistent with any other.
If you have some representation of phase space.
Yeah.
And you look at all the states that comply to the condition A, which is, say, ice cube.
Yes.
Right.
Yeah.
This is set A.
Yes.
Now, I'm going to look at a state that I would, a macro state,
Right.
which I would typically expect states from this
To evolve into.
5 minutes later.
Yeah.
And that is a set B,
Yes.
which is going to look something like this.
Yeah.
It's the silent circle. Right.
Right.
Now, do I expect these trajectories to evolve to B?
Yes.
Yes, most of them.
Because most of them,
Yes.
in fact, I can look at all of them if I
Yes.
want to,
Yes.
and they will occupy some weird.
Yes.
So this is,
Yes.
Right.
Exactly right.
yeah, so this is T evolved.
Right.
Okay.
Right.
So every point of this corresponds
Correct.
to that. Right. So I got the uniform distribution over these ones.
Yeah.
And they evolve into a uniform
Yes.
distribution over these ones.
Exactly right. Yeah. The
Exactly.
contradiction is
Wait,
between the claim.
Wait, let him finish.
Okay.
So, of course, that is a very different from the set of the ensemble I would construct.
That's
by
all
taking-
we're saying.
Over
Yeah.
B.
Yeah, that's exactly right. That's all that's being said.
Okay, well, what is being said is that there is a difference between two ensembles. That is not saying there is an inconsistency.
No. Here's the inconsistency. Okay. Here, every word will be correct, and it's a slightly different way of saying exactly what we've been trying to say. Okay. What would be inconsistent, okay, would be to imagine that there could be a single ensemble of systems, okay, that start from here, evolve to here, okay, such that the frequencies of microstate realizations when they were here are correctly described by this, and the frequencies of macrostate realizations when they're here are correctly described by this.
Yes.
That's what's impossible. That's it.
Sure.
But as
That's it.
Wayne has pointed out, you don't need to blame this system for that. You can make the same mistake, whatever it is, just by letting a gas expand in a box without, and it's
Yes,
the way
of
that
course.
works.
But that's a particular example of exactly this.
Yeah.
This is the gas in one corner, this is the expanded case.
I'm following this and saying if I'm missing something really basic what the controversy is, but think about it. You're just saying something as simple as this, aren't you? I've got a set A, which has a certain measure, and a set B, which has a certain measure that's bigger.
Right.
And I've got a measure preserving dynamics that takes points in A and points in B, but it doesn't take the uniform probability distribution in A to the uniform distribution.
Exactly.
Yeah.
Right.
But that seems so elementary. I mean, of course.
Okay. Do you think this?
So we all agree.
No, but I mean,
Of course, it's the problem part that I'm not getting. I'm saying, yeah.
No.
But if you took seriously the idea that somehow or another applying the uniform probability
Right.
to
If
B
you
was the
thought-
correct one.
If you thought that the following was a law,
Of course, but
okay.
it can only, I think that my intuitive response is, of course, a certain probability distribution can only be the correct one if all you know about the system is that it is state A
Okay.
or in state B.
This wasn't intended to
In
take.
the present case, we are knowing much more.
Yeah.
We're knowing
That's
the
right.
system is in state B,
Right.
and
Right.
it has been in state
Exactly
A 10
right.
minutes ago.
Exactly right.
That's a difference.
This wasn't intended to be a deep point.
No.
Indeed, I forgot to say it until you said, "What's the third problem?"
Yeah, I know.
But
We're still worried.
yeah, that's exactly right. That's exactly right, and I think everybody is in agreement.
I remember Shelley Goldstein once says, one thing we know about the standard probability measures is they're wrong.
Right, that's right. That's right. Okay, good. What can we do about all of these problems? Okay. Is there any sort of simple single stroke, okay, that can somehow set all this aright? And this is an interesting question about the history. I don't know if Boltzmann put it quite this way, although I can't imagine that he didn't have something like this in mind. The first person I know of explicitly putting it this way is Feynman in this, not in the Feynman lectures. What's this more popular book of lectures? The Fundamental Structure.
What? The nature of the physical world, or the character of physical law, or
the character of physical law,
yeah,
something like that. Right. So Feynman certainly very explicitly says it there. Okay. Here's what you can do. Add another postulate to your basic set of postulates. Okay? That at some early time, say the beginning of the universe or something like that, the macro state was some particular thing. We know, we can say at this point what various characteristics of it probably were. It had very low entropy. It was, the sort of state that cosmological research is presenting us with in more and more detail, so on and so forth. Okay. Add this as another basic postulate of your theory. You can call it the past hypothesis. Okay. And say, or another way of saying the same thing, the probability distribution we should put over possible present microstates of the world is not related to its macro state in this way. Okay? It's the one that's related to its macro state by the standard distribution conditionalized on the claim, which is going to make it a very different distribution, okay, that it was once here. Everybody with me? Okay. This, once again, we're making a Jewish proof here, okay? But the idea is this potentially can set all of these problems aright in one stroke, okay? It can validate rather than contradicting what we take our photographs and memories and so on and so forth to be evidence for, okay? It can get us out of this reductio or cognitive instability or whatever the right name for it was that we were talking about a few minutes ago, okay? And it emerges as the right place to apply the unconditionalized uniform statistical postulate. Everybody with me here? Okay. Good. So, if this picture is roughly correct, the way the sort of fundamental scientific picture of the world looks is that, at least in the classical case, it consists of three distinct elements: the microdynamical equations of motion, the statistical postulate, and the past hypothesis. Okay? You put those together, you get rid of the unwelcome or reductioable or destabilizing consequences of what we had without the past hypothesis. And it looks like this is a kind of simple stroke for setting everything, for making all these problems go away. Yeah?
So maybe I just don't understand the mathematical force behind time reversal invariance being part of all of the initial ingredients. But it seems to me to be a simpler solution to say that we shouldn't expect a bunch of time reversal invariance in to always spit time reversal invariance out, and instead to say that the segmental thermodynamics that we get out only is time reversal. It doesn't speak to the past. It doesn't have any. I think it doesn't say anything about what was going on in the past. It's forward-looking. It could be time reversing. It could do what you're saying there, or it could not. And then the cosmological evidence that we have that suggests that the entropy is lower in the past gives us reason to suppose that, in fact, that we are somewhere.
So let me see. It sounded like there were a couple of distinct questions there. Let me see if I can disentangle them. I mean, there's one simple logical point. No time direction in, no time direction out. Okay, that is, if you start with a bunch of premises that don't indicate anything about what's future, and what's past, or don't make any such distinction, you do any number of logically permissible operations on them. You're not going to get anything about future, or the distinction between future and past out of them. That's just a straightforward logical point. Okay, I wasn't sure if I understood you in the beginning. In the beginning, it sounded like you were doubting that, but that I'm not sure what the grounds for I'm not sure what the grounds for doubt could possibly be. That where are you going to get it from? I mean, where the operations of sort of logical equivalence of going from one step in induction to another don't add any asymmetries between future and past that weren't there in your premises. So as a logical point, that seems trivial and clear. Now there are plenty of people in the literature who say things like, okay, it works toward the future, but not toward the past. So use it toward the future, okay? And don't use it toward the past, okay? That seems to be taking a sort of instrumentalist rather than a realist view of these probabilities, okay? That seems to be, if it's really true that this or something like that gives you the frequency, gives you the degree to which you should expect this to be the microstate, okay? And if you really believe in the microdynamical laws, then the degree to which this or that, the degree to which you believe this or that is the microstate has to match the degree to which you believe this or that was the past trajectory, okay? Because we have a completely deterministic dynamical theory, okay? So if you're not taking this seriously as a claim about the degree to which you ought to believe that this or that was the microstate, but you're just saying to yourself, making that assumption is a good way of predicting toward the future, okay? Then you're using it in a fairly radically instrumentalist way rather than in a realist way. And as with all instrumentalist sort of instrumentally useful procedures, it's just going to raise a further question about why that works, okay? About what it is about the actual structure of the world that makes that a good way to do the calculation. It's always an easy option to say, and a natural option to say, the reason this assumption makes it a good way to do the calculation is because this assumption is true, okay? But if you're taking this assumption as true, then you're committed to the rest of its logical consequences as well.
Could I add a small remark? it is, of course, an option to say that thermodynamics is only looking towards the future and should only be used for that purpose.
Right.
And and I agree completely with you, that would be a fairly instrumental outlook. It also, of course, conflicts with the way people use thermodynamics. The famous example is that very early on, Kelvin.
Sorry, could you speak up?
So very early on, Kelvin tried to estimate the age of the sun from observations or estimates about its temperature and the way and how its radiation, and how long it could have been doing that before it cools down. And unfortunately, his estimates were way off, but that's only because he didn't know about nuclear synthesis as a source of energy. But apart from that unfortunate slip and the conflict he got into with the geologists, this way of using thermodynamic laws and projecting histories backward instead of towards the future seems imperfectly accord with scientific standards, and it's a very
right. I mean, once again, certainly it could, and there are people who say, okay, the lesson of this, okay, is to be instrumentalist about this and just use it toward the future. That's an option. If one takes that option, my next question is always going to be, okay, then this isn't really what I wanted to know. I wanted to know how the world is, such that this turns out to be a good way of doing the calculation. And once again, unless there are obstacles to doing so, the natural thing to do seems to be to say, this is a good way to do the calculation because it's true, okay? And then you ask what follows from it's true, and all kinds of horrible stuff follows from it's being true. So then you ask how you could modify the claims about what's true in such a way as to hang on to this part and get rid of this part, okay? And the claim is that there is a way that there is a certain set of commitments you could hold about what's true, okay? That will give you this, get you out of this, okay? And everything is hunky-dory, yeah.
So I get that you can make this move. I'm curious as to why, upon reflection, you think the more natural thing to do is to introduce, say, this additional past hypothesis.
Yeah.
And rather not say to yourself, well, hang on a second, maybe there's something fishy about the way in which I'm thinking of the statistical postulate.
Look, I don't. So, the question would be, I mean, that's a matter of sort of scientific theory choice, and as always, yeah, it's a function of what's on the table. I mean, that sounds like a perfectly reasonable research program. Okay. The question is, what's it going to? So you're going to want some different way of characterizing this. Okay. That is, this could be thought of as a way of characterizing this. Okay. That is, you just say the correct probability distribution to put over this is the one that's uniform with respect to the standard distribution, conditionalized on this. Okay? That's a claim about the probability distribution now. So if it's just a matter of using the language a little differently so that it becomes clear that it's a claim about the probability distribution now, that's easy to do. But that's presumably not what you want. You want some other natural sounding claim, okay? A claim that doesn't refer to other times or something like that about the probability distribution now that's going to give you what you want. And presumably you want it to give you what you want via the existing dynamics, okay? The dynamics you're holding on to, the classical dynamics. Good. That's a well-formed question. It's not clear how that might look. That's not to say that one couldn't come up with such a thing. That sounds like a really intriguing research program. Let's, talk to me in a year or so. Tell me what you got. I certainly don't want to. There wasn't any claim that this is the only logical option. Okay, the claim is that this is a simple and clean one. okay, which as far as one can tell, looks like it'll work. Yeah.
I think it's what you said anyway, but it does seem very important to stress that for this to work, that it can't be the case you've got three ingredients, the underlying micro laws, this authoritative measure, and the Hart hypothesis. It seems to be crucial that the objection probability measure just is the old kind of measure conditional on the Hart hypothesis. But
are those different?
Well, if they were separate ingredients, you might say you have no right to believe the Hart hypothesis because the standardized story of why you shouldn't believe these possibly false memories about the past.
Right.
You want
No. Yeah, you got to have them all at the same time, but I think they're logically independent of one another. But I mean, it doesn't matter if you want to. Indeed, here's a way to put the whole thing. Okay, I'm sorry, Dave.
Oh, I just said if you want to phrase it as logically independent, you just want to do something like say, okay, the probability hypothesis is that the correct probability distribution in the microstate conditional on whatever other macrostate constraints there are.
That's right. It's the uniformity. That's right. And then you've got you've got two other conditions on the macrostate. What you presently see in the past hypothesis. Okay. And then you've got the dynamic. Right. Yeah.
I just want to make a remark and see if anyone ever talks about this. The assumption going into the initial setup where you have all of these fluctuations is that you've already had a very long pass to the universe.
Oh, you mean the Boltzmann setup?
Yeah, the Boltzmann setup.
Okay, that's not the one that's being.
No. I just want to go back one step.
Right.
Because I confess, I never paid much attention to that particular literature because I always assumed that you need calculate the probability that you've got a fluctuation in which just the air in this room moves over to one side.
Right.
You've got a time period that is enormously many more orders of magnitude than the age of the universe that's coming out of cosmology. Now that doesn't mean that.
But Boltzmann was presumably assuming that the age of the universe was infinite.
Yeah.
Right.
Yeah, no, I know. But I'm just pointing out there's that oddity there. I'm assuming that oddity in fact does not nullify the whole thing because in that universe you might have a fluctuation that looks like it came from as it were a Big Bang.
Right.
Right. And so that's why we still have to take this seriously, even though the basic setup needs some, it's really a question, but that's actually the reason I've never, up until now, paid much attention.
To the extent that I understand what you just said, I think I agree. But I'm not 100% sure I understood.
I just want to make a historical note. I think some of the students don't know this, but we do. Boltzmann actually proposed that in two places. I don't know how serious he was, but in a letter to Nature and the Lectures on Gas Theory, he actually proposed that the universe is vast and has been around for an incredibly long time, and most of that time it's in equilibrium, and there's occasional rare fluctuations, and we find ourselves in one of those.
Right. Right. Yeah. Let me. You know what? I'm just.
But I don't think he drew the inference that we should take ourselves to be near a entropy minimum.
Well, doesn't he talk about us being on the upgrade of one of these?
No, that's different from being at.
Yeah.
No. Of course he didn't say. No. My claim is that Boltzmann understood essentially all of what I've said.
But he didn't actually then say, well, we should take our what seem to be memories to be illusions.
But doesn't he talk about? I don't know who. This is a good question. Certainly, there are scenarios which people now refer to as Boltzmann brain scenarios, where you point out, look, the fluctuation that just realizes this room. Or that just realizes my brain now is much more likely than the fluctuation that takes us back to what we consider a cosmological. Didn't Boltzmann talk about that?
Actually, a few weeks ago, spent some time researching the history of that. Boltzmann didn't seem to have that realization.
I see.
It was Eddington who pointed out that who said, well, you actually shouldn't take yourself to be any fluctuation larger than what's required for the existence of a mathematical physicist.
Right.
And it was Martin Rees in one of his popular books that said that we should take ourselves to be no more than a frame.
I see.
It was Andy Albrecht who coined the phrase Boltzmann frame.
But certainly Feynman knew about this stuff.
Yeah.
I mean, Feynman talked about this stuff very explicitly. I figured Boltzmann knew about it.
No. Well, in the speculations that Wayne just mentioned, he describes as a vast world, vast universe,
right.
which has been in existence for forever,
right?
And it's predominantly in equilibrium,
right?
But then every once in a while there must be fluctuations, and sometimes these fluctuations might be, say, in the size of say a galaxy,
right?
And we might happen to be living in one of those.
Right.
And in rough shape, fluctuation would, of course, be some peak going up both ways. And now, if there are sentient beings alive in that situation, he argues that no matter whether they're living on the upside or the other side of the frame, their sense of temporal orientation would always align with the approach to equilibrium. So that for all these sentient beings, entropy would go up.
Right.
And
good. Look, I'm approaching a third of what I wanted to say in this lecture. So my goal is just going to be now to finish the 1/3, which I ought to be able to do in a minute or so. I mean, I had intended to devote 2/3 of this, and maybe I'll devote part of what I say on Friday to it, to extending this into an account not just of thermodynamic time asymmetries, but of two other very fundamental kinds of time asymmetries that we encounter in our experience of the world. The asymmetry and the kind of epistemic access we have to the past and the future, and whatever asymmetry it is exactly that we're gesturing at, however ineptly, when we say things like, by acting now, I can affect the future, but not the past. So I think I will try to talk about those a bit more in my second talk. Let me just finish up. Let me just finish up this picture now with a couple of very short remarks. Suppose we buy all this, and we take it realistically in the way that we were just discussing. Then, what these three things, so we've got these three logically distinct elements. The microdynamics, the statistical postulate, and the past hypothesis. Okay. Note that these three together give you a full probability distribution over trajectories of the world, okay, which are going to assign a definite numerical probability to every formulable proposition about the physical history of the world, okay? There aren't any such propositions about which a probability distribution like that is going to be agnostic, okay? So that it's either the case that one of the elements of this picture is false, okay, or it's the case that there's some principled sense in which those three elements together. Now, mind you, we have no clue in any kind of detail what these elements are. That is, it's the business of theoretical physics to determine what the microdynamics is. We have no clue what this. We have plenty of clues, but that's certainly a radically unsettled question. Whether it's string theory, whether it's this, whether it's that. Those are questions about the microdynamics. There's vis-a-vis the past hypothesis. I guess the way of determining that is going to be as a convergence of two distinct lines of investigation, a sort of observational line of investigation and a theoretical line of investigation. The theoretical line of investigation is the following. Ask yourself, as a sort of mathematical question, given the microdynamics, given the statistical postulate, what kind of claims about the initial macro state of the world would have the feature that the world we see is statistically typical of the trajectories that would have come out of it. That's the theoretical question. There's a separate observational question. What do the standard observational techniques of cosmology tell us is likely to have been the initial macro state of the universe? What's required in order for a program like this to work out is for those two to converge with one another, okay, in some way, okay? So that's what there is to say about the past hypothesis. But anyway, once all this is in place, you've got a contraption that assigns a definite probability to every formulable proposition about the physical history of the world that's agnostic about absolutely nothing. So that either this is false or in some principled sense, it's the entirety of natural science, okay? Barry Lower and I have been sort of fooling around with this kind of probability distribution for a long time. There was a Coen Brothers movie about 3 or 4 years ago called A Serious Man. Really good movie if people haven't seen it. Where the protagonist has a psychotic brother-in-law who's constantly scribbling in the notebook. And when he's asked what's in the notebook, he says it's a probability map of the world, and he calls this notebook the Mentaculus. So we've taken to call it the what? He calls it the Mentaculus. And so we've taken to calling this probability distribution the Mentaculus, because it seems to answer to the description of a probability map of the world.
Okay, I've heard reservation then about this Mentaculus,
right?
Because the empirical, as we said before, the empirical evidence we have is that if there is a right probability distribution, it's among those that, that give these right things.
Yes.
And I can convince.
Yeah, let's say a little more about that.
Because I might be convinced that the probability measure you just described, namely the one that is as uniform as possible, conditional on what we know, including what we think would be true about the past, does the work.
But there are lots of others.
But why should I pick that one as the Mentacular one?
Absolutely right. So there are several. Here's let me say a tiny bit more about this. Look, take a simple case. Forget about the whole universe for a minute. Take a simple case of a gas in a box. Okay, it starts out all bunched up over here. You want to know what it's going to do. Here's an important observation. Okay, it's not merely that on the standard measure, most of the states are non-perverse states that are going to expand and fill the box. It's the case of the perverse state. So suppose this is the region of phase space associated with this bunched up macro state. Okay. It's not the case that the perverse states have a small volume, but they're all concentrated, say, in this region or something like that. If you just reflect a little on the structure of the microdynamical equations of motion, it becomes obvious in the way we were saying before that these perverse states are radically unstable, okay, under small changes in the microstate. So they're not bunched up in one region. That would imply that the property of being in perverse state is relatively stable, okay, that the other states near a given perverse state are perverse states too. That's not the case. The perverse states are radically unstable. They're scattered in unimaginably tiny clots, okay, throughout this region, okay? And it's the case that over even very small distances, if you move off a perverse state, you're in a non-perverse state, okay? So, if you reflect on that, and if you reflect on the fact that since almost all the other states evolved deterministically in almost identical ways toward equilibrium, okay? All the probability distribution is really doing for you. As I said at the very beginning, you see how nice the structure of this lecture is. All the probability distribution is doing for you is giving you a reason to neglect the perverse states, okay? And Wayne is pointing out, absolutely correctly, that there are lots of probability distributions that can give you license to neglect the perverse states, okay? Any probability distribution whose variation in space, okay, it occurs over distances that are large compared to the distance between a typical perverse state and the nearest bunch of non-perverse states is going to do the trick just as well. Everybody understand me? Okay. Good. Is there any reason then why we would pick the uniform one? Well, maybe simplicity or elegance or something like that, but that's not a particularly compelling reason. Okay. There are lots of other probability distributions that could do the job. There's no reason why the considerations I just went through here vis-a-vis a box of gas don't scale up to the universe as a whole, okay, and apply to the statistical postulate over the probability distribution. So you could do lots of things at this stage. You could say, you could have lots of different arguments. I don't have any particular commitment to how these arguments come out. You could say, maybe there are theoretical reasons for choosing the uniform one, simplicity, elegance, blah, blah, blah. Maybe not. Maybe there are reasons for choosing some other one, okay? Or maybe there are reasons for adopting a picture like this. You consider the full set of probability distributions that would do the job, okay? And you say that the propositions to which your theory is committed are all and only those on which all those probability distributions agree, okay? One of the statements on which they'll all agree is that you can neglect the perverse states. They'll agree mostly, presumably, about routes through thermodynamic space and relaxation time. So there's a lot of freedom you could have there. There's a lot of ways you could formulate this. People tend to depend on the uniform one just because that's the simplest one.
Sure, I mean, the uniform one is in effect the microcanonical distribution.
Right.
That then turns into the canonical distribution for the subsystems, and you've got to get exactly that canonical guy, or you don't get.
Hang on, it's not the microcanonical distribution. These are not entire energy hypotheses.
Oh, right.
These
I'm
are
sorry.
particular
Right.
It'll be awfully close to it for equilibrium.
Right.
I think that's exactly right. And I think that's what we should do. And if we did do that,
What's what we should do? You mean take a set?
Yeah,
right.
And if we did that, and then said, okay, well then which ones are out of that set? Which ones are we going to use in our calculations?
Right.
If I know that everything in that, for the things that I want to calculate, everything in that set gives me the same, approximately the same result as the canonical one.
Right.
Well, I'll use the canonical one because it's easy to calculate.
That's certainly a way to do it. There might be an argument, like I say, it might emerge on certain views of what extra empirical criteria for theory choice are, that the uniform one is the right one, but I don't know how to.
Just to clarify, I'm now curious, just to get clear in my own head, on the relationship between the uniform probability distribution that you talk about and the microcanonical distribution.
So I don't know the Gibbs way of doing it well at all.
Can I ask a very specific question?
Yeah.
Is your distribution simply the microcanonical?
I don't know.
Restricted to, okay.
Yes, it is.
Yes, okay, all right. Then what I said earlier still obtains, because I don't think anything other than that uniform distribution conjecture.
But that couldn't. But then that couldn't be true.
You can put a pretty generic distribution across the energy hypersurface of a combined system and still get the canonical one out as the reduction. Well, those reduction theorems don't rely. Theorems too strong.
They're not very sensitive.
They rely on any characteristics regarding it. They just rely on a not crazily spiky. It's some of the exact resulting quantum mechanics have improved in the last few years. Very, very lenient bounds on what you can do with that.
There's some classical results too.